Tony, it's a great pleasure to speak to you today. It's always a great pleasure. You know, we've met before, but it's a great pleasure to meet you in person. You were one of the original developers of CaearII. You then started a company, Paulin Research Group, which published NozzlePRO and FEPipe. You've sold that company a couple of years ago, and now you're very heavily involved with several developments within the B31, ASME B31 community. Perhaps we can go over a few of these today, Tony, and I'd love to, do a little deep dive where possible. Before we start, how are you doing, Tony?
I'm doing great. Thank you very much.
Yeah. So you mentioned B31H, you mentioned B31E, Appendix W, and B31J, obviously.
Right.
Maybe as a quick starting point, you can, maybe one sentence for each of those, tell them a little bit what they are in the first place.
Right, and they all link together in terms of evaluating the stress and the capability of the piping components.
Let me pause there for a second. Please realize that this interview with Tony is part 1 of a 3-part series, and that part 2 and 3 are exclusively available for anybody listed on our piping mailing list. So if this interview is relevant for you, if you're involved with industrial piping systems in any way, make sure to click the link in the description below or the icon in the top right and to join the mailing list. And as a bonus, the first 1,000 people that join the mailing list using this link will receive a free seat to the live workshops that we run with subject matter experts on EngineeringTrainer.com. So pause the video, join the piping mailing list, and then let's head back to the interview with Tony.
Right. And so B31H starts with the burst test. What is the pressure capacity?
Yeah.
And so in the later, as we've matured as an industry, finite element analysis has taken over some of the scaling responsibilities. We tested older components that were made in using different manufacturing processes.
Yeah.
So now we have to adjust for the newer manufacturing processes. So we're setting up the standard to use, in part, finite element analysis for the scaling, and then to set up the rules so that we can address the different components that come in and the more unique components that we need to set up the burst test rules for.
Yeah, so that would be B31H,
that's
like
B31H.
fully focused on burst testing.
Right.
Yeah.
The pressure capacity, really the pressure capacity, how you test for it and what rules you should follow when you test for it.
All right. How about B31E, which you're also involved with?
So B31E is for seismic and rapidly reversing dynamic loads. So seismic waves, let's say, that have frequencies higher than 2 hertz, or that give responses of piping systems greater than 2 hertz, are considered rapidly reversing dynamic loads.
Right.
But so also is water hammer.
Yeah.
So the same approaches that we use for seismic can be in part used for water hammer loads, because that was always an issue, is what is the allowable for a water hammer load?
Yeah.
And the difference for rapidly reversing is it tends to be more like a thermal load. So it's strain limited, displacement limited, not force limited.
Right, yeah. All right, we'd love to hear more about that one, but we'll go into it in a second. You also involved with the Appendix W work. What is that related to, Tony?
Okay, Appendix W is part of B31.3 now. And so there had been some questions about how the use of Section 8 Division 2 welded fatigue curves came into Appendix W of B31.3.
Right.
And so there were some small issues with how those constants were calculated. And so we took the opportunity to take all of the data that Chris Hinnett had originally brought together, plus additional test data, and put those together in a, he used that to essentially define the code or the equation that's used in the front of B31.3 in the body of the code for the allowables today.
Yeah.
Where 6n to the minus 0.2 was changed to 20n to the minus 0.3.
All right.
So that's in the body of the code today. Yeah. But the documentation for it had never been extended to the current number of tests we have. And so all of that, the tests were extended to the present day, and then all of that was put in Appendix W so that we're not relying on Section 8 Division 2 Part 5 anymore, but rather we're relying purely on piping fatigue tests.
Hi there, a quick reminder. If you also want to receive access to part 2 and 3 of this interview with Tony Paulin, make sure to join the piping mailing list using the link in the description below or the icon top right. And be quick, because the first 1,000 people that join the list using this link will receive a free seat to the live workshops that we run together with subject matter experts on EngineeringTrainer.com. So take a moment now to join the list, and then let's jump back into the interview.
Right.
So we've taken all the piping component fatigue tests we've found since prior to Markl
Wow.
and put all of those in one place, and then are publishing that, and that's been recommended for B31 Appendix W.
Right.
So it all ties together, more or less, B31J and B31 Appendix W.
Yeah, and I mean, if we then segment to B31J, which is related to the stress intensification factors and flexibility factors.
And the sustained stress indices. So all loading components, plus occasional, are in B31J. So B31E relates to the new technology or the new approaches that have been recommended in B31J.
Right.
And B31J was developed prior to 2020, so that was after B31.3 put in the sustained stress indices. So there's a little mismatch to the terminology.
Yeah.
So B31J immediately now needs an update of that terminology.
Right.
And then there's always new things for SIF development.
Yeah, yeah. Before diving into you know, each of these four topics, there's a lot of development, like research, new data that will pull up that you organized, gathered, but also made like through new research. How does this work impact the work, let's say, the day-to-day life of designers and people you know, doing pipe stress analysis?
Well, in one case, for B31J, for example, is it expands the applicable data. So you come in and there's these limits. T over T must be between these ranges, and D over D must be between these ranges. And so as we run more tests, we can see that, these actually apply to a broader range of data.
Yeah.
We can see when we have tests on base metals, for example, versus weld metal. We can see where the variations start, so we can see how the conservatism increases or decreases, and we can make adjustments to the rules for these particular components.
Yeah.
Because that's the big thing, is piping is a component-based. Bend, T, reducer, straight piece of pipe, support, Section 8 Division 2 pressure vessel, but the rules tend to be more general for stress states in general, where we're focusing on stress states and components. So the standard deviations are a little bit different.
Yeah, yeah, and I mean, there's a lot of, you know, new data. There's a lot of plots that will show. Is it such that people will use that data in their projects directly, or will it impact them through the code more or less?
It will impact them through the code, absolutely.
Yeah.
And hats off. Originally, a lot of the testing was done in the United States. In fact, most of it here and then in Britain before the war. But now, since Fukushima and since the number of the earthquakes in other parts of the world, India, the colleges in India, Dr. Gupta, has developed a lot of very good technology and is, in fact, is coordinating with us to say, well, I would do it this way, I would do it this way, here's how we break these time histories down.
Yeah.
So we get information from Korea, information from Japan, where we never got that before.
Yeah.
So there's a lot of data flooding in, and it's good to see the world coming together to try to tie all of these SIFs together.
Yeah.
Because once the fatigue strength of steel should be the same in Germany, in England, and Holland as it is in the United States.
It's the same physics.
Yeah,
Exactly. All right, well, let's dive into B31H. I suggest maybe you can introduce the topic a little bit and start with the slides.
Okay. Can we? Unfortunately, there's some general information that I would like to go over. That people, and it's a little bit interesting because this box represents the parameter space that you have to test.
Yeah.
And a lot of people will make the mistake where they'll say, I've built a system like this before.
Right.
And so I know what it should be for everything.
Yeah.
But the problem is that when you develop code rules, is you have to cover the full parameter range. Right. Every range of the type of system that you're evaluating. B31.5 is different than B31.9, is different than B31.3, it's different than B31.1 for a reason. Yeah. So you have to make sure you cover all of the different aspects. High temperature, cryogenic, large D over T, small D over T, different types of supporting systems, cold. I mean, all of these things have to be included. Plus, the most difficult thing in the original development of B31J was all of the sizes, because all of the sizes hadn't been covered. Most of Markl's tests were done on 4-inch size-on-size fittings. Yeah, well, 4-inch size-on-size fittings it's D over T of around 20. Yeah. You know, the largest D over T is 100. Yeah. So whenever you consider the code rules or looking at the tests or thinking that you've got something that I know how to do this, as soon as you move into a different area in the parameter range, that's when you have to stop and say, okay, has the code covered this for me appropriately? Yeah. And the reason I say that is because the world is moving in the direction of hydrogen. Yeah. And hydrogen has a whole different whole different parameter space, let's say. Yeah. So you have, just because you have tons of experience in refinery work or power work, Hydrogen is different.
Yeah,
So
it's
you
hard to generalize.
Got to make sure, right, that you study the particular industry and the application that you're moving into.
Yeah.
But that's the code responsibility, and it's our responsibility to
Yeah.
do that when writing the rules.
Yeah, but I can imagine, you know, for example, from what I know from the B31J, you know, you have all these different equations, a lot of, you know, coefficients. It looks quite comprehensive, you know, especially if you look at it for the first time, all these D over T, T over T, all these ratios. That ties into the point that you're making now. In order to generalize those rules for all these different systems and situations, yeah, you need to fill the entire, you know, as the cubes in this slide, let's say the entire dimension space.
And another, sort of to follow up with that, is people would ask us, was the old Appendix D bad? I mean, were the
Right.
rules, should we go back and look at these things? And in general, our answer is no, because they cover the core work perfectly.
Yeah.
I mean, even though they're very simple equations, just like we said, it covers the core work as you would expect to need to do it within
Yeah.
enough accuracy and safety.
Yeah.
What happens is, for certain parameters, when the T over T ratio gets very small, when the D over T ratio gets very large,
Yeah.
D over D at 0.7 is a difficult part of the parameter space. When you're in those areas, the codes were off.
Yeah.
And so that's where we made the adjustments. And that's where you'll generally see these small notes describing these unique situations.
Right. Yeah. Yeah.
And the same is true with the allowables. People say, well, Markl was wrong, and there's these new Hinton curves that are right, but they cross in the middle.
Yeah.
So as long as most pipe stress is in the middle, you're using exactly the same allowable.
Yeah. 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 Okay. Yeah. Thanks. Yeah.
But earthquake is low cycle, and so now you're outside of where the Hinton and the Markl curve cross. So
Yeah.
now you need a new set of equations, which is what's in the code now.
Yeah.
So it covers what Markl did well, but it also covers low cycle and high cycle well.
Yeah. Yeah. Exactly. Like more the let's say outer edges of these dimensions. Yeah.
But when you're in that space, a compressor, low cycle pump, any of those things, you're in the high cycle range.
Yeah. Exactly.
So how does it impact the user? Well, it's expanding the ranges where he spends more time, and we're, in the case of the high cycles, is we're moving the allowables down to where they should be,
Yeah.
because the allowables previously were too high.
Yeah.
And we can fix that. And similarly on the low cycle range, now the allowables are higher, so when we go into something like for seismic, if we're doing seismic addresses low cycle fatigue. So not only are the allowables higher than Markl, but the strength of the pipe is stronger. And we've known that now because of more tests that were done.
Yeah.
So we're providing higher allowables for the user.
Yeah. All right. All right.
So there will hopefully be a big benefit, because less supports, harder to route the pipe, high temperature pipes, not so easy to route anymore, because you don't need as many supports.
Yeah. 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 All right.
It's an exciting time to be a pipe stress engineer.
Yeah. 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 I can imagine. Yeah. Yeah. Yeah.
Okay, we keep going.
Yeah.
The next thing that's sort of a general item to mention, and I think a lot of in my era, and perhaps in yours some, is we didn't focus on reliability. We didn't focus on risk. We didn't focus on, is this dangerous? What part of this controls the risk, or what part of this controls the reliability of the system? Because that's where we want to focus. So what we do now is we focus strongly on the pipe and the bends and the T's, but now there's all the special things. How you build the supports, how you take these special pipe-to-pipe couplings, clamps, mechanical fittings, these things have to be focused on more tightly, because you don't want the specialty item to control the reliability of your piping system.
Right, right. And like, help me out here a little bit. What specialty item exactly are we talking about? Like specific T's that weren't used before?
Mostly it's pipe-to-pipe joints.
Right.
So B31.9 piping systems are filled with mechanical couplings.
Right.
And there's multiple ways to design for these mechanical couplings. Some of them are free, so they move a certain amount before the gaps close.
Yeah, exactly.
And then they tighten up. And then you have to evaluate the strength.
Yeah.
And what we're doing now, because the pipe is stronger, is we're requiring really these fittings to be as strong as the pipe, because the allowables are going up. So the loads on these things are going up.
Yeah, yeah.
So we have to be right about how strong they are.
Yeah, yeah. I can also imagine that new tools, especially the wide range usage of finite element analysis, makes it that you can go into that level of detail.
100%. One of the keys about B31J is it shows you the test procedure. And with the test procedures, especially for sustained loads, is it's a very easy test to reconfigure in a finite element calculation. Producing fatigue stress or predicting fatigue stresses with a finite element program is different, especially when you're dealing with welds. Yeah. Predicting collapse is really pretty easy.
Right.
So yeah, we can get much better results for much larger D over T's, for much wider ranges of geometries. And all you have to do is follow the procedure in B31J.
Yeah.
Appendix D.
Yeah.
That's it.
All right. Yeah.
Okay, so there will be more reliability. I mean, everything we do now points in the direction of reliability for the user, which is the LRFD approach, which is what most people see in Section 8 Division 2, Part 5, is LRFD. So you see the partial safety factors on all the loads.
Yeah, yeah.
And so you'll start seeing more of that now with the piping load cases.
All right, isn't that usually all organized in the safety factors on the allowable? Like the let's say risk and reliability?
Well, what we're doing is, in fact, I mean, the first thing you do when you start setting up a risk and reliability based code is you tune it to everything you did before that you believe was safe.
Yeah.
So we essentially start with the allowables, but then with the loading, so you use, because people are familiar with the allowables, you set them up and leave them as they are.
Exactly.
But then it's with the loading that you put the partial safety factors on.
All right.
Like if we don't know something about seismic, then the partial safety factors are bigger.
Yeah,
If
yeah,
we know
that makes
something, then
sense.
the partial safety factors can be smaller.
Hi there, me again. Please make sure to take a few moments to join our piping mailing list if you also want to gain access to part 2 and 3 of this interview with Tony Paulin. And as a bonus, the first 1,000 people that join the list using the link in the description below receive a free seat to the instructor-led workshops that we run together with subject matter experts on EngineeringTrainer.com. So pause the video, join the list, and then let's get back into the interview.
That's the benefit, is that where you have a high pressure stress, you know the pressure.
Yeah.
So the variation of the load is going to be small. With seismic or water hammer, for example, you don't know the exact magnitude of the load.
Yeah.
So you can still design it to the same reliability, providing you recognize that you don't know the load that well.
Yeah.
So the coefficients of variance or the partial safety factors
Yeah.
are just larger.
Yeah. That makes sense. Yeah.
It's simple. One of the conditions that happens in the low cycle range is that we're used to fatigue, and we're used to primary loads, and we're used to occasional loads where to pressure and weight we add seismic.
Yeah.
And then we still use the same allowable, which is put a load on a cantilever, and if it bends too much, then it's failing.
Yeah.
But as we said before, with water hammer loads and seismic loads, these are rapidly reversing, so they behave like thermal.
Yeah.
So with thermal, it's not a collapse. With thermal, it's fatigue.
Fatigue. Yeah.
So when we go to fatigue, now we have high loads in the low allowables.
Yeah.
So there's another phenomenon that we didn't have to concern ourselves with before so much, and so it was never really discussed in piping, which is ratcheting.
Ratcheting. Yeah.
So what ratcheting is when you look at the very low cycle fatigue life, it's the low cycle is adjusted by the amount of the primary load. Pressure's higher, weight's higher. Even though it doesn't cycle, it affects the fatigue life.
Yeah.
So you have to consider the ratcheting mechanism, which is a function of the weight load and the pressure load, and how it interacts with the cyclic load, which is what you see from the Bree diagram.
Yeah.
I mean, this started with the nuclear industry and has been implemented as part of the nuclear industry's requirements 1960, 1950,
Wow.
but we never caught up to it.
Yeah.
Now, it's in Section 8 Division 2, but it's a little bit hard to see. I mean, there's ratcheting, and ratcheting's discussed, and it's a little bit vague, and it used to always be 2SY or 3SM, and we compare that allowable, and we think we're okay.
Yeah.
And we are. I mean, generally we are. But what we're doing is 2SY and 3SM are down in these regions.
So just for my clarity, what are the axes here that we're looking at?
This is the thermal stress, so the range of the thermal stress,
Right.
or the range of the seismic stress,
Yeah.
or the
any
range,
any cycling load basically.
any cyclic load. That's rapidly reversing.
Right.
Wind, it's not.
Right.
Because wind, even though it's reversing, it's not rapidly reversing. So it acts like a primary load.
Yeah.
It acts long enough to actually cause collapse.
Right.
The rapidly reversing water hammer loads act long enough to cause fatigue to contribute.
Yeah.
And so what happens is, here is the cycling load, and then this is the membrane load.
Right.
So you would find pressure down here, you would find weight, anything that doesn't vary. So what you see is this line is the EG equals 0 line. So as long as you're below this line, then you never get any ratcheting. So what you see is that when the membrane stresses are very low, you can cycle into very high stresses.
Yeah.
And so that's exactly what we want with seismic loads or water hammer. So you have plasticity, but we don't have many cycles.
Yeah.
So the system's going to be fine. And that's what historically we've seen since 1985. I mean, they did all these tests in 1985 and said, use plasticity allowables, use plasticity in terms of the analysis, because it gives you a far more accurate and reasonable result. The tests that were conducting allowables or yield strengths measured with strain gauges that didn't fail the pipe on the order of 10 times yield, 20 times yield.
All right. Oh, really?
Because you cycle it so few times.
Yeah.
And that's exactly what this diagram tells you.
Yeah.
If the pressure's high and the weight stresses are high, nope, you jump into ratcheting very early on.
Yeah, exactly.
So it's very easy to make a ratcheting calculation.
Yeah.
And we've done it in the other codes for years and years.
Yeah.
And so now we just introduce it as simply as we can to B31E.
Right. All right. Is this already in there in the latest edition?
It's in our draft versions.
Yeah, for the next
So
version.
So we hope that the next version will be published in 2027.
Hmm.
But it'll be released, and then is this more applicable data? Some people would say this is a more applicable way to conduct a stress analysis.
Yeah.
The way that it's set up is a bit unique because you make the calculation the way you make it now,
Yeah.
and there would usually only be, because of stress intensification factors,
Yeah.
there will only be a few high stress points.
Yeah.
So what happens is you can take this approach and go to those high stress points
Yeah.
and address them individually.
Yeah.
So you can say, well, really, this is happening here.
Yeah.
And then you say, okay, so really we're okay.
Yeah.
For an earthquake that's going to occur every 2,000 years.
Yeah. Exactly. Yeah.
So so it's very economical and I think easy to understand way because the rules are simple.
Yeah.
And
Yeah.
you only address the places where you have a problem.
Yeah. That makes sense.
And the nice thing is we don't have to do the tests because as we were saying earlier, in India they're doing a lot of testing, in Japan, Korea they're doing other. So these tests are all from those locations.
All right.
So we've run a few in Houston to make sure that our numbers match theirs,
Yeah.
so that we know what's going on. Everything matches perfectly, and they just continue to pump out data and test for different components, so we cover the full parameter set.
Yeah. Yeah. Yeah.
So the world is sharing and making the codes better.
Nice.
Yeah, it's very appealing. It's a very pleasant job, I think. Let's see. And then should we step through these? A little
Yeah.
bit?
Yeah. I think it's very interesting.
Because this is B31.3,
Yeah.
Appendix W.
Exactly.
So what's happened now is we've taken all of the component piping data and put it together on one fatigue curve.
Yeah.
And so that is what you see here. So this was been in the base code of B31.3, and now it's getting put in B31.1 and all of the other codes because previously the slopes were wrong.
Yeah. So just from my understanding, like this is the obviously the fatigue curve.
Yep. Stress range here, number of cycles here.
Exactly. We see a lot of black dots. Maybe you can explain us a little bit. Like, I mean, Markl must be in there.
If you've looked at Markl long enough, you see the Markl tendency. This is Markl's tendency right here.
Yeah.
And so this is why his slope was so shallow. Is if you extend this set of data points, it comes out here.
Yeah, exactly. The extrapolation is different. Yeah.
So it says it's too high. So it give you. I mean, clearly, if you say this is the allowable and the real allowable's down here, you're predicting a fatigue strength that's too high.
Yeah.
But on the flip side is the prediction of the fatigue strength that's too low.
Yeah.
So in reality, I mean, these are all physical tests.
Yeah.
So these tests were all, this is where the failure occurred.
Yeah. Yeah. So Markl is in there, but also you mentioned the Japanese contributions, the Indian contributions.
Japanese did a ton of contributions on bends, all in the low cycle range.
Yeah.
So we can populate this range nicely, come out to 10 cycles of failure.
Oh, really?
So, I mean, yeah, so it makes us know that for the bends and the base metal, using the I factor to adjust for the weld metal tests,
Yeah.
is we still get a straight line.
Yeah.
And our standard deviations are on the order of 0.2 or so.
All right. Yeah.
So,
Yeah. So what we see here is basically the complete set of, let's say, all the data, also outside of the data points that Markl brought up.
100%, because Markl would say stop. Realistically, Markl would stop here, and Markl would stop here,
Yeah.
because some of his low cycle tests were very difficult for him to run.
Yeah.
So the results, when you compare them to the existing data, you say that's not right.
Yeah.
And in part because when he was running 4-inch pipe, he started with standard 4-inch pipe. So to run a low D over or a high D over T test, he had to bore the pipe out.
Yeah.
So he's boring out a 4-inch pipe, and he looks at it and he says, well, the center's not right.
Yeah.
Okay, so then he makes a T out of it and tries to test it. It's okay, and then the results don't fall on the chart, and it's not surprising they don't.
Yeah. 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 Yeah.
But yeah, we were very happy with this. So this has been introduced now in Appendix W of B31.3. So we now have a full basis for what's in the base code and what's in the B31.3 Appendix W.
Yeah.
Because, for example, for offshore, with the wave loads, is you have very high cycles.
Right.
And in some plant applications, where you have batch processes where you may cycle 3 or 4 times a day,
Yeah.
refrigerator systems where you heat it, then you cool it, then you heat it, then you
Yeah.
cool it.
Yeah.
You'll have cycles out here.
Yeah.
And now we've got much more data out there and feel more comfortable with the results.
Yeah. 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 Would you say, I mean, especially for that region, the allowables are reduced when it comes to the stress range? Is that correct? Given the fact that the Markl's data would run higher than the new lines, could you comment on that? Is that an issue? Is that important?
It's interesting because, I mean, Markl had tons and tons and tons of data,
Right.
but then his company was sold and the data went to the company.
Yeah.
Then that company was sold, then Markl wasn't involved anymore.
All
Then
right.
eventually the story is the company that bought this, there were rooms of paper that nobody knew anything about, that
Yeah.
they didn't do anything with, so it was thrown away.
Right.
So a lot of Markl's data was thrown away. We have clearly the test results in the papers, but very little extra data.
Hmm.
But so as a problem with this, for example, is now we know exactly where the data comes from, because this test, the high cycle and the low cycle test, is for more realistic numbers.
Yeah.
To get back to your question is why was Markl shallower? Nobody knows, because the papers were lost in
Right.
part, and when Markl ran the tests another fellow in the 40s, but Markl in the 50s and later 50s, the material quality wasn't as high.
Right.
So there was in particular more sulfur. So the sulfur impacts the fatigue life.
Yeah.
Plus, because we don't have any drawings of his tests, we don't know how strong his fatigue tests were.
Yeah.
So if the fatigue test is weaker than the pipe, then as you start to flex the pipe, then you start seeing the machine move also. So the data is a little bit off.
Yeah.
And Rotobaugh adjusted for that in later testing. So they would put extra braces on. We put extra braces on our machine when we went to really large deal T. And so now we think we've solved that problem, but that could have caused the slight change in the slope of the curve. Well, it changes from 5 to 3,
Yeah.
so a little bit important.
And do you feel that this high cycle range, given the fact that Markl's fit through the data ended up being higher, given higher possible stress range, allowed stress ranges, is an issue for let's say those high cycle systems? Now we learned that it should have been a bit lower. Maybe you can comment on that.
Well, what we think tends to happen is that high cycle systems, the people know it's more of a problem.
Yeah.
So you do special things with compressors, you have a higher grade weld with the compressors, you have a little bit more inspection with the compressor, a little bit more radiography.
Yeah.
For us, the buttering of the welds, you're more careful with the welds. You tend not to use OLETs because people think, okay, OLETs are bad because the strength of the nozzle is so high, creates higher stresses. And so you do things to avoid the problem.
Yeah.
And so there's changes to the curve slope even in Appendix W, that at 7 million cycles, you can change the slope.
Right.
And so you get a little bit shallower, which says that, these places with the high cycles, the stresses really can be a little bit higher, and still have the safety factor that you want.
Yeah. All right.
So the people that know, that they design the systems properly.
Yeah.
Now, because the curves suggest exactly the way it is, you can use the curve and get reality.
Yeah. Get even closer. Yeah. All right.
But just so B31W, so that's we think useful. And so with the B31.3 codes, is everything is being tied together. There's more test data continually coming all the time. We add it to the curves for piping components. So it's a piping test, and that's what goes into the piping code for the allowable.
Yeah.
So, and they're spreading the B31.3 equations that were not in B31.1. Like previously in B31.1, there was only a single I factor.
Yeah.
The maximum I factor from in-plane, out-of-plane, and torsion, you took the maximum, used it for everything.
Yeah.
Now they've said, well, okay, we know that's not really right.
All
so
right.
the B31.3 equations are moved into B31.1.
Yeah,
and
yeah.
the allowables are moved in because, we know what the test data shows us.
Yeah.
This is test 2 failure.
Yeah.
So you can't argue with that.
Yeah, you basically build so much confidence in the data and these equations that the adoption is easier as well. Yeah.
And it's from so many different places by so many different researchers, and they all come to the same conclusion.
Yeah.
So it was something that we never really had before. It was never available to us.
Yeah.
But this is an example of what happens with ratcheting. So all of these tests are run without pressure,
Right.
without high pressure certainly, and without weight loads.
Right.
Very little weight loads. But as you add weight loads that are closer to the allowables, what happens is the fatigue life drops.
Yeah.
So there's an interaction between the fatigue strength and the primary loads. So and that's the ratcheting.
Yeah.
So and we believe we can.
And that's only for low cycles.
Only for low cycles.
Right. Yeah.
Only
as we
for the
just
low
saw.
cycles.
Yeah.
Right.
Yeah.
Right. Let's see. Oops, over here, isn't it? Oh, that's not so important. That's not so important. Well, let's go to burst testing.
Yeah.
So with burst testing, the problems with burst testing were that we didn't know the scale factors.
All right.
So the people say, well, 2 diameters, 3 diameters. We can go 3 diameters taller with a welding tee or with a reducer.
Yeah, just from my understanding, we're talking here about the B31H, which describes the procedures that manufacturers, for example, have to follow in order to do the burst tests.
Right, right.
And they don't want to test all the components of all the sizes.
Right.
So they do some and they scale them with certain rules.
Right, right. Yeah. And so if you have a 10-inch, you can say that it's good. That 10-inch test is good for 20-inch.
Yeah, yeah.
Okay, but even though they use different ways to squeeze it, different ways to form it, different radii, different manufacturing, completely different for these sizes.
Yeah.
Because what you can use to squeeze a 10-inch, that machine's not good enough for a 20-inch.
Yeah.
So you have to use a much more powerful machine.
Yeah, so they used to generalize over all these different manufacturing procedures. You know, we do a test for 10-inch and we generalize it to the other sizes. That was the scaling, you know, that is currently in place, to my knowledge.
And the principal scaling is for the crotch radiuses and the crotch thicknesses.
Right.
And to the code developments, I mean, the tip to that to the code developers is, I mean, they recognize that this is an issue, but it's a difficult issue to solve because in some cases the scaling is there, in some cases it's not there.
Yeah.
But the manufacturers are really the ones responsible for it, but they don't know.
Yeah.
And so I think what we found out is that you can either go back through the Buckingham Pi rules for scaling that's very confusing and setting up the parameter ranges, or you can use finite element analysis.
Yeah.
So if the finite element analysis predicts the means within a sufficient accuracy, and you can run a finite element analysis for a larger geometry or smaller geometry, and it predicts the same means that you expect to get, then you say, yes, I can use this as a scaling tool.
Yeah, okay, so that would be the manufacturer using FEA to prove that they're on point as well for a 20-inch, and then they can generalize perhaps.
Right. And I think as importantly is we're trying to use the same rationale to reduce the number of tests required. Right. Because if the finite element analysis predicts the means, and you take the exact material properties, and you get one test falls right on the finite element result, there's no reason to run 3 more tests. Because one of the reasons manufacturers don't run all the tests, because it's expensive. And it's very expensive, especially in the higher sizes. And it's more dangerous. So we're making things safer, we're making it cheaper, and we're improving the quality. Not we, but I mean, I think this approach, because finite element analysis was never really available before. And now it is, and now people are comfortable enough using it. Plus the nonlinear rules have really matured in the last 10 to 15 years. So the finite element programs themselves are more competent and capable. It's a good time to be alive, a good time to be a piping engineer.
Yeah, for sure.
But so yeah, with B31H is we recognize now that we want to pay more attention to couplings because there's not one coupling. I mean, a bend has a common shape. You know, T has a common shape, so every more or less makes it the same. But couplings, mechanical couplings, are made a variety of different ways. Clamps, rubber, mechanical seals, high pressure, low pressure, high strength, low strength, and everybody makes them differently. And so it's very difficult to come up with one single set of rules or one single test procedure.
Right.
Because what is strong in one direction for some components is completely free in another component. So setting up the rules has been very difficult. But what we're trying to do is draw attention to the couplings. So that when you put a coupling in a piping system, in general, the coupling is as strong as the pipe. And if it isn't, then you make a determination to add more supports, make sure that because of the configuration around the coupling, it's strong because it's not going to get the loads that are put on the piping.
I'm not familiar with couplings myself too much, to be honest. In what type of systems would they be used?
The B31.9, I think we talked about that before. The B31.9 is all of these mechanical couplings. So it's very easy to route the pipe with the mechanical couplings. And so buildings, go to all commercial buildings, if you walk, you'll see pipe, you won't see a weld. You'll see a mechanical coupling, and another mechanical coupling, then another mechanical coupling. And in high-rise buildings, when there's a water sprinkler goes off or a fire event, all this flooding of the water in the system. What about the transient loads? How much calculation do they make? How do these things support the rapidly reversing dynamic loads? We don't know.
All right.
But we need to know. I mean, that's the testing is, we're making recommendations to the tests so that they don't stop prior to yield. They have to stop at failure. Because it's the failure that we relate all those safety factors to.
Such that the couplers become you're confident that they are as strong as the pipe.
Or protected, or there's secondary containment for it. In a plant, for example, is if you're confident that this piece is going to fail and you don't need it for a firewater system, for example, you build a trench under it. Or you put something over it so that it fails, it leaks, and then it goes someplace safe. In a hospital, you don't have that. You know, if one of these things fails in a hospital, very dangerous. Well, not dangerous, I mean it's bad for the hospital. So, but yeah, so the couplings they're special. The couplings are a little bit special. The unique thing for us was the material, because the materials were different. Everybody used B16.9 used the PD over 2T equation equal to tensile stress as basically switch that around to get pressure on one side. That was your burst pressure.
Right.
But that equation doesn't work well for stainless. So it was not, I mean, when the B16.9 basic rules were developed, stainless hadn't had welded joints in the code yet. So in the long time ago, stainless wasn't there. So the rules were developed back before stainless was available. And so they just carried on, and we kept using it. But you won't, if you take a stainless steel pipe and use a B16.9 burst pressure, it won't pass the test.
Oh, really?
So straight pipe won't pass the test.
And how is that addressed?
Well, let's see. We come down, I show you. Right here. So what Chris and I did is we set up a series of tests, and we can show some pictures of the bursts a little bit later. But here's 4 carbon steel tests, relatively large D over T, 12-inch pipe. And then here's the stainless steel test. So this is the calculated burst pressure over the actual test pressure.
And these are just like pressure burst tests?
Right. You fail, pressurize it up until you lose pressure capacity, until you get from what's inside the pipe to outside the pipe, because that's the danger. And so here's all the carbon steel. So you can see the ratios. So the ratios are all very close to 1. Here's the stainless steel.
It drops down.
20% less. So there's a material factor now in the new B31H for stainless and copper nickel. We've been helped with some copper nickel tests, and we'll be running more tests with other manufacturers.
But this is on primary load and primary, let's say, checks. How does this impact, you know, the work people do? So does that mean that the allowables are lower with this properly implemented?
What you're trying to do is, you can imagine if you do a burst test, the burst test is probably the best way to know the pressure capacity. You know, you can do a finite element and get a rough estimate, but maybe you've missed something in the finite element model. Maybe it's a little bit thicker than what you hoped it was going to be in a crotch, and a little bit more brittle. And maybe the welds weren't quite as good as you hoped, and you can't put that in a finite element model. So what we tend to do is we want people to run at least 1 or 2 burst tests. Make sure that you have a good feel for the pressure capacity, especially for things like couplings, which they do anyway. But then also be able to run a finite element calculation so that it syncs with what you think the strength is going to be. And this helps to make sure that for those stainless steel components, they don't just say, it's the same, but you actually have to correct for that. Right, and we know that it's going to be 20% different. And so when we see the 20% different, we don't think it's because the model's bad. I mean, we're identifying where the difference in the pressure capacity comes. But what happens now is it's not so much for straight pipe, of course, because nobody really tests straight pipe. It's for the T's. Now they're making T's thinner. Since the 1990s, post Markl, T's have been made cold formed rather than hot formed. So hot formed T's are notably much thicker generally than the matching pipe. T's today, there are certain parts on the T sidewalls that are thinner than the matching pipe. So you think, a T can't be thinner than the matching pipe. But indeed they are. So at what point can you say, yes, this is okay, and what point is it not? Because this is the way they're manufactured. And because the manufacturing process is considerably different than hot forming, you have to look at all the changes in the manufacturing process that may be sensible to damaging the material. But that is in the end all captured within those burst tests, and hence the pressure capacity of the component. Burst tests and continued inspection. Continued inspection. So you have to look at the surfaces, places that we didn't know we had to inspect before. Now we have to visually inspect these places, because a big part of the cold forming process is to start from a straight piece of pipe, and then you have these large T-presses, and put a huge compressive stress on it. And then you put the opening for the branch, and then you put a large pressure inside. As the compressive stress, buckling compressive stress picks up, so the pressure essentially pulls the branch out into the opening.
Yeah.
And then the thicknesses they have to be on the sidewall of the T, because the Blanchbrook was within 87.5% of nominal.
Yeah,
So they're
thin.
thinner than nominal rather than thicker than nominal.
Yeah,
And the pressure failure occurs in the crotch.
Yeah,
So it's the crotch thickness and radius that are key.
Yeah, which is completely different from the thicker T's through.
And what happens is, because the problem with the cold forming is that you can crack the T's because you've got huge strains in these things.
Yeah.
Now you heat treat them afterwards so that these strains go away. But while you're making them, they will crack. So cracking during this high forming process is difficult.
Yeah.
And the cracking occurs in the crotch. So you do these things to prevent cracking in the crotch that make it weaker for pressure.
Right.
So, okay, well, the manufacturer has to balance these things.
Yeah. But in the end, again, they will run those pressure tests in order to prove pressure capacity.
Right.
Yeah.
And you have to make sure that the tests are run, at least some of the tests.
Yeah.
And as you go from manufacturer to manufacturer, one manufacturer has a different size T-press from another.
Yeah.
And has completely different experiences from another.
Yeah.
And the key to the manufacturers is knowing how to increase the pressure when you increase the compression.
Yeah.
So it's all very, not secretive, but it's proprietary for them making a good tea for you.
Yeah. In the end, they just need to show, those pressure capacities that they are proven.
Right.
The details behind it, they might not show, of course. Yeah.
And that's the difference between EN 10253 A and B. Like A is the thin T's.
Yeah.
But if they have the pressure capacity due to the burst test and the inelastic finite element modeling, we say, yeah, it's okay. Doesn't have to be stronger than the pipe.
Yeah.
But that's why the Bs are always thicker than the matching pipe. So if you buy type B and you think, well, it's as strong as a pipe. Well, so is A,
Yeah.
but it's only based on this simple hand calculation. Conservative hand calculation says A is too weak.
Yeah.
But if you test it, if the manufacturer does his job properly, then it's okay.
Yeah, in the end, they explicitly differentiate between those situations, which the ASME doesn't do, to my knowledge.
Right, yeah, not at all.
Yeah.
Not at all. It's a B16-9 stamped, you're good.
Yeah, exactly. Yeah.
And as long as it's greater, the inspector doesn't know if the crotch should be thick or not. It's hard for him to even measure the crotch.
Yeah.
So for him, he puts the thickness gauge on the sidewall. It's within 12.5% of nominal. He's happy.
Yeah.
So it's less than the matching pipe.
Yeah. And this work contributes to those protocols that the manufacturers have to abide to as per B31H.
100% is what we're doing, is trying to help them recognize what's critical in terms of the pressure capacity of the component.
Yeah.
So, yeah, it's Chris Ennett and Ron Hopt and I are. It's exciting work, and so we continue to complete it. And once B31E is finished, which is our objective now, we hop right back on B31H and try to finish it as soon as possible.
Right.
With new versions of B31J, so they all continue to improve and use the same technology moving forward.
Yeah. A lot of work to be done. Yeah.
But it lets people use what's being made.
Right.
And if it's safe, you can use it.
Yeah.
Just because it's not overly conservative, you don't have to go over conservative to say something is used.
Yeah.
Which is, to some extent, what's done with the Type BT.
Yeah.
But that's really B31H mostly. Let's see. As part of that, we try to predict where the burst occurs.
Where, for what type of component?
For what type of component, and with the straight pipe. Because for straight pipe and large diameter straight pipe, you can't buy seamless pipe.
Yeah.
So you buy welded pipe.
Yeah.
So what is the variation in the welding? I mean, where did the 12.5% come from?
Yeah.
It's not uniformly 12.5%. I mean, this shows you, this was some 6-inch...
Which, maybe you can explain this plot in a bit more detail.
So what this is this is 6-inch copper nickel pipe.
Right.
Okay, so very common on shipboard piping. So a lot of copper nickel pipe for the shipping industry.
Yeah.
So what this is a variation of the thickness around the circumference.
Okay, so vertical axis is
This
thickness.
is a variation in thickness.
Yeah.
So what we see here is there's a 9.3% variation in the thickness around the circumference.
Right, so horizontal axis is simply the angle around the circumference. Right.
And so what happens is the pipe is not, the inside of the pipe is not concentric with the outside of the pipe.
Yeah.
And that's because the pipe is seamless. But we want to use seamless pipe.
Yeah.
Because seamless pipe is good because it doesn't have a weld.
Yeah.
Okay, well, but seamless doesn't have a center. Doesn't have a concentric center.
Yeah.
And 9% off.
Right.
So there's a part that's thin.
Yeah.
So where you put your T's, but that lets us, plus there's a weld in it.
Yeah.
You know, there may or may not be a weld in it, depending on how the manufacturer wanted to make it.
Yeah, but this is very much depending on, you know, batches, manufacturers, you know, the process itself.
100% the batch process, how the material's heated, how uniform it was when they plastically deform it at temperature, how the billets go through, or these punchers that go through and make the pipes, how they can keep them centered.
Yeah. Have you been able to predict it, where the burst occurs?
Oh yeah, absolutely.
Yeah.
I mean, I'll show you some pictures later of the burst tests. And what we did is we drew yellow lines on where we thought, because we measure these first. Right? So you measure this in the beginning, then you measure it at the end.
Yeah.
Because what you would expect is, does it just get thin where the crack occurs?
Yeah.
Where it bursts, or does it get thin uniformly?
Yeah.
All the way around, part of it.
Yeah. Yeah. Yeah.
But we'd never seen that. We've never done that before.
And like, could you make a general statement about it? I mean, my first, you know, guess would be there where the wall is thinnest,
Is where it fails.
The burst occurs.
And if that's in line with the weld seam, of course.
Right. Yeah.
But okay, so we didn't know these things. We wanted to see how once it starts plastically deforming. I mean, so if you're using yield, you're out here.
Okay, so these are the test results.
This is the actual test results.
Pressure
So this is
versus
the pressure versus time.
Yeah.
So you can more or less think of this as pressure versus how much water we've pumped into it.
Exactly. Yeah.
So it's linear, 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 so everything is elastic. Now it starts becoming plastic. So now we're beyond yield, but we keep adding, it expands like a balloon.
Yeah.
And this is all the carbon steel tests and all the stainless tests.
Right.
And then the damage occurs out here.
Yeah.
So when you think of the damage, what's the damage in a tensile test? So in a tensile test, you pull, it starts to neck down.
Yeah.
But that's okay, that's still part of the geometry. That's like the Play-Doh.
Yeah.
So it just gets smaller, smaller because you're pulling it more.
Yeah.
But then it starts to become damaged.
Yeah.
So then you start getting microvoids.
Yeah. Correct.
So then when you take the temperature or take the load off, you can't solve that problem with post-weld heat treating.
Right.
Or any type of heat treating because it's already damaged. So up to here, we're fine. There's very little damage. The damage occurs out at the end. But so we don't have to be as concerned if we're in this part of the chart.
Yeah.
So.
But I mean, it would still, like, this is for burst tests at the manufacturer's side.
Or the owner. I mean, the owner gets a ton of pipe delivered.
Yeah.
And some of it you inspect the welds, and sometimes they're okay, sometimes there's more porosity there. Should you accept it? Well, you run a burst test.
Yeah.
I mean, if they're simple burst tests with very easy to follow rules, you're not rejecting pipe that you shouldn't reject.
Yeah, but going back to that previous plot, just to make sure that I understand, is in that region where the curvature is already happening quite a lot, that would still be okay.
You haven't started necking until here.
Yeah.
You haven't started reducing the wall thickness significantly until here.
Yeah.
So it's okay. I mean, so you're buying yourself this pressure to this pressure.
Yeah, of additional margin.
And we think, and this is what the failure is up here. This will be the failure pressure.
Yeah.
Not something based on yield, which is what area replacement rules are more or less based on.
Yeah.
Is yield. So, and this shows essentially the same thing. This is the same plot, but this is local. Then as you start getting even more local to the plot.
We're basically zooming in, is that?
Yes, basically zooming in on the end. This is where you start getting damage to the material.
Right.
So it's out here that the material gets to be damaged, and then you start to see gross distortions.
Yeah.
So here it's just not, I mean, I hate to say that you don't want to blow the pipe up to these pressures and keep putting water in it to have it keep it like expanding like a balloon. But you haven't really damaged much in these lower strain ranges because we want to be able to use strain as our friend, just not too much strain.
Yeah.
But so it's so now here's the test pieces. So these are the stainless pieces, and there's the carbon steel in the background. That's Glenn Woods, who's a very famous guy in pipe stress. He's the one that designed our fatigue test machine.
All right.
So back in the 70s and 60s, he designed that machine for WFI. And then they used it and then sent it to us.
Yeah.
But here are the burst pressure tests.
Here's the test, yeah.
So these are the tests at Smithville. So all of the fabrication facilities are over here. So we put a vessel course down as protection. Yeah. So all of our equipment was on the other side, and then we did the burst tests on the other side of the vessel. Yeah. There's large fields over here.
Yeah.
So we could get around it and take some interesting pictures and photographs.
Yeah.
Some of these. There's the tests. And there's still things to try to explain. Here's the center of the pipe. Yeah. Why didn't it fail in the center of the pipe?
Yeah, I don't know.
I don't know either.
Yeah.
Here's the center of the pipe. Why did it fail in that quadrant?
Yeah.
So we have to go back and look at all these detailed thickness readings and all that. There's still a lot of data to be processed for these. Mm. But here, this is just an example of material variations. Right. So the code gives us minimums. Well, hopefully our minimum is down here, and then all these variations are above the minimum required thicknesses.
Yeah. This is UTS versus temperatures. And yield,
and how they change.
Yeah.
So you can see so where is the safety? So when we try to make the probability estimates, is the material quality and where the safety factors are. Yeah. And the fact that the ASME sets these borderline minimums, that you can't go below these minimums.
Yeah, and this gives an idea of the spread in the different material samples.
Right, and how much stronger than the minimum that you really are.
Right, yeah.
So, but here's some of the post-thickness measurements that we took. So we were interested where the pipe thinned, how it ovalized. And then this was us predicting.
Just to jump in there, sorry for interrupting, like post measurements, by that time the thickness can be changed.
That's what this slide is.
Yeah. Oh, sorry. Yeah.
Is how much the thickness was reduced, so that once you have a plant event, water hammer, something like that, but everything is okay, you can go out and measure the thickness.
Right.
And this is the M2. This is the M2 factor from Section 8, Division 2, Part 5, or Part 3. Yeah. So M2 is published. So you can put it in with the initial thickness and get some estimate of once you've measured the actual thickness, you can know how much strain the pipe was exposed to.
Ah, right.
2%, 1%, peanuts.
Yeah. And how to think of that as in, like, what is acceptable and what would not be acceptable? How would you think?
I would say that the rules these days are still being developed for large strain. Right. Because for pressure vessel heads, you can have up to 5% strain in the knuckles. Yeah. But that seems like a high number. Yeah. Twice elastic slope, 2 to 3% strain. Still a high number, much higher than 0.02% or 0.2% strain.
Yeah.
But we know we can plastically deform these things and they can still carry the load. So. But it's not so easy usually to make estimates for straining.
Yeah, I can imagine that an owner, when something like this, let's say a water hammer event happens or an earthquake, and they do the measurements after, they see a certain amount of strain, they have to be very comfortable with the decision to keep going. Basically.
Exactly. Yeah. And this is just one way to help do that.
Now, thanks for watching this first part of the interview with Tony Paulin. I hope it provided you with lots of new insights and value. The second and third part of this interview are exclusively available to any professional listed in our piping mailing list. So make sure to use the link in the description below and sign up. And as I said before, the first 1,000 people that use the link receive a free seat to the instructor-led workshops, the technical workshops that are live and that we run on EngineeringTrainer.com.